Hello to viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about how do we cool down Mumbai or basically any other coastal city. So let's dive deep into it. So what exactly is the problem? Well, be mindful, this will apply to almost every coastal city. Mumbai in India, basically, or Bombay, as you used to call them, it's ancient city. They are not old, they are ancient. And in India, they started with fishing community. Almost most coastal city starts with that. And now, as of now, when I'm making this video, they have reached megapolis status, meaning the amount of people living here is huge, bonkersly huge. Like how huge? Well, because we are talking about India, you have to understand there are almost, give or take, 200 countries on this planet. 150 countries have less population than this puppy. So we are talking about around 20 million people. Basically, you can feed whole of Netherlands here and we'll still have space left. So dense. And it's getting hot. Again, there is a double conundrum here. First, you have global warming that is making it hot, and then you have urban heat island that is making double hot. So if the planet temperature goes up by 2 degrees, this goes up by 6 degrees. So that's the problem. And it's creating what we classify as feedback loop, meaning the hotter it gets, the more we do things that makes it even hotter. The more hotter it gets, then it's like the more we do, and it's a feedback loop to hell. So fundamentally, it's not a desirable situation or sustainable situation. So we have to solve this, because again, let this be very clear, I'm focusing on Mumbai, but this applies to every coastal city. And again, even international, but coastal city have a solution. So this is the part of problem that we are dealing with. Now, why exactly this problem is this bad? Well, these are the other metropolitan in India, like Bangalore, Hyderabad, Kolkata, Delhi. And you can see that like from 2007, they have started to cook, slowly cook, and even more cook. Now they are ultra cooked. So it's really, really bad. Now, why is this? Why the heck this happens? Well, you have to understand, air is a poor heat conductor. It's not aluminum. It's not vapor chamber. So it's like heat happens here, it gets equilibrium very quickly. No, it's a almost insulator. In many designs, we actually use air as an insulator. So it's not a very good conductor. Second, the concrete mass that we put on these places, they act like what we call heat soaks, meaning they absorb heat. Basically, photon comes in, it heats it up, and it just keeps eating it up, and its temperature slowly starts. It's not a reflector. It's not like twink. No, it slowly eats it. Basically, it goes inside, and then nighttime it starts to dump the heat, meaning the cooling that we used to get during nighttime in this sort of places, they are overwhelmed by the heat rejection of all the concrete mass, meaning the overall temperature, day and night temperature, both has elevated. And on top of that, making it even worse, because the more people you have, the more structures you have, the air circulation is really bad. That's why if you look at airport and you really look into it, the tarmac gets really hot during daytime, but it also gets cool. Now, why the heck it gets? Generally, airports are not surrounded by other things that impede airflow. So fundamentally, all these things combined makes them oven, so to say, really, really bad. So sun puts a heat during the day and air fails to dump the heat adequately overnight, and it creates what we call runaway effect. So if global warming is hot, this is ultra hot. Let that be very clear. It generally gets multiplied by 2 to 3 degrees Celsius in some scenarios. So it's really bad. Now, what is the outcome of this? More people install air condition, which makes it even worse. Why? Well, the air condition is just a heat pump. It leaches heat from your inside, basically indoor temperature, dumps it outdoors. But here's the air, again, same rule apply. Air is not a good conductor, not a great conductor. It will not just like equilibrate to whole planet. It will dump in there and it will stay there. But imagine this was a big system, or more, hundreds of people are doing this. So brick by brick, the air temperature, that like, hour over hour, that air temperature will start to rise up, because all of you are dumping basically a space heater there. And penalty of that is your insulation, basically the chamber walls you have, it's not perfect. It will have some leakage. Again, if outside temperature is 40 degrees Celsius and you want to maintain 25 degrees Celsius indoor, your basically walls, insulation have to stop it. But here's the deal, that insulation cannot do its job quite well if the outside temperature goes to 55 degrees Celsius. So that means the leakage, basically the leak heat that is coming inside goes up exponentially. Meaning you reach a point where this is like, I can't do. It's basically inherently trying to run a refrigerator whose door is open. So it can't work. And okay, what do you do when it can't work? You put more energy into it, more load into it, and the cycle continues. So it really turbocharges its own demise. So fundamentally, AC dumps heat outside. Hot outside simply means more heat leaking inside. More heat leaking inside equals more and more and more self-containing cycle. And originally we thought cooling towers would be a solution for this, because while air can take enough heat away that it can cool down some small loads like 100 tons, but the moment you are talking about 500 ton or 1000 ton or 10,000 ton loads, yeah, air is not good enough. So we utilize cooling towers. Now cooling towers are basically air conditioner. We call them chillers, and the chiller have a hot end. That hot end generally have liquid running through it, generally water, or in some scenarios glycol. So that water goes into a cooling tower. In that tower, it could be generally a closed loop scenario, so you'll have a closed loop. But to cool that coil, because again air cannot take enough heat away quickly enough, so we spray them with water. And again, if it's cold enough, cool water recirculates. But if it's not cool, which again not cool, in those sort of water just evaporates away, which we call latent heat of vaporization, meaning it leaches a lot of heat away with surprisingly little amount of energy. And it does allow us to have very high concentration of heat loads, meaning you can run servers. Otherwise, you would not be able to run servers. Hospitals, hotels are kind of low load, but servers, hospitals, basically gyms, things of this, basically school, colleges, yeah, you can't cool them. It's just too much. So we generally utilize cooling towers in those sort of structure. Now they do work, but they drink water like there is no tomorrow. So that also creates a electricity scarcity and a water scarcity. Plus, we recently started to find out, originally we used to think that there is no penalty there. It's just that we recently started to find out, assume you have magical scenario where water is not an issue, which again, not in India, but let's say you are in a situation where water is not, it makes this effect worse. Like how it can do that? Well, thankfully it does go up very quickly, but once you have lot of people doing it, it still starts to create a curtain, so to say. And if you studied your school correctly, you would have remembered water vapor is a greenhouse gas, meaning the nighttime cooling effect starts to get impeded. Now we have not reached that cook-off point, but there is a cook-off point, meaning this just delayed it. Basically, using cooling tower just delayed the same effect of this. And again, if you are dumping too much water, that local region will start to become humid, which again will make everyone else's life miserable. So urban heat island effect is really getting out of hand, and it's multiplying. So basically 2 degrees gets multiplied by 3 degrees. So things are getting out of hand, and we really need to fix this. So the first tool that we have to utilize, the first step, so to say, first stage, is district cooling. Now district cooling is basically the idea that instead, like same way you provide services like water, sewage, you provide cooling. Now cooling simply means cold water, but here's the deal, you do not take the cold water, meaning, oh, I have cold water coming through. No, it's just as a loop. It's a sealed closed loop, and the liquid runs through a heat exchanger. That heat exchanger gives you cold end. What do you do with it? For example, let's say hotels, they do not generally have bonkersly high heat loads. In those sort of scenario, you can literally have a water running through the building load side of it, and then you can just run a fan coil unit. Many places do that. So fan coil unit is just, it allows you to dehumidify, it allows you to cool the structure down, everything is fine, and then the water that is now warm comes back to the heat exchanger leaches the heat, dumps it into the cooling loop, and things continue. So that's one very cost effective, easy way of doing it, and your energy cost is very little. Then what if you have some heavy load, let's say computers, office buildings, you're consuming some serious power. In those sort of scenario, water may not be adequate enough to create temperature delta that you are seeking. In those scenario, people could use basically the chiller and dump its condenser into this. Basically, its condenser's loop goes here. Same thing happens. And again, most of the time fan coil units are good enough, but sometimes you may require a bit more that extra oomph. So that can be done. And why would companies do that? Because again, it's a service, they have to pay for it monthly, it's a rental. So why would they do that? Well, here's the deal. Benefit of doing this does not matter where you're looking at, be it USA, be it India, be it Dubai. Wherever they are doing it, the benefit is you are reducing your water consumption. Basically, chillers can only work as long as they have cooling tower. Cooling towers can only work as long as they have cooling water, and water is consumable, and they consume a bonkersly large amount of water, meaning we are reaching a point where people are drinking very little amount of water with bathing and all that jazz, but they're burning a lot more water because of the cooling. So that cooling cost is serious. It's like day one, you do not care. Like day 500 is like, oh my God, I'm burning so much profit just to run the water. So that goes away. Done, gone, shift deleted. Another is lower bill. Why lower bill? Well, this is a Indian system where you have coolant coming in at 5 degrees Celsius, leaving at 14 degrees Celsius. And this is a plate heat exchanger, so kind of efficient. So you're going to dump 15 degrees Celsius and extract 6 degrees Celsius. Now, here's the deal. That's cooler than what you generally want to do, even in a server. So what does that translate to? That translates to your compressor is working in positive delta, not negative delta. Meaning, generally, whenever we are running air conditioner is trying to maintain a negative delta. Basically, energy does not want to go from 25 degrees Celsius to 50 degrees Celsius outdoor, but we are forcing it. We are negative, like go. We are forcing it. That's why it consumes so much energy. But here's the deal. What happens if you want to cool something now and the cold end, basically the condenser end is already cool. It's already cool. Meaning you want to cool your room to 20 degrees Celsius and the liquid is 15 degrees Celsius. Your COP on any refrigeration loop goes up exponentially, meaning barely getting 4, you can easily get 8, and some chiller designs can easily touch 10. So that's how we generally do this. So you not only you will save money on your electricity bill, you will also save a lot of water bill, eliminate it. So that justifies enough of it that every country is slowly getting into this, that we have to do it. And because of the system efficiency, that you have a one dedicated center whose sole job it is to cool the damn thing, they do a much better job than you can do in your unoptimized structure. Basically, you build a building first. They build a building, they build a cooler first. So it's much more efficient. And because instead of having hundreds of small compressors, you have one giant one, the efficiency advantage is massive. And you can utilize dangerous things here. For example, ammonia. Ammonia is not suitable for indoor places, but here it's a professional place. Only qualified people go there. So it's almost like how you have substation. So there you get extra benefit, all the benefits. Basically, you may not be able to afford chillers that have compressors that are running what we call maglev bearings. But again, they can afford it because they are cooling such a large area. So brick by brick over the system, you change nothing else. Even if this consumes water directly, like a Dubai design, you still get energy savings still. Like energy goes down, your water consumption goes down. And this is an American design where they did double dipping, where they're like, hey, instead of running the compressor during daytime where it's very hot, electrical grid is basically crapping out, what if we run it at night? And instead of creating cold water, we just create ice. And so they have ice batteries inside these buildings, basically hundreds of kiloliters of ice, and during the daytime they shut off the compressor and just cool water circulates. So that's how they are getting efficiency gains. And in all scenarios, you will get far more efficiency if you change nothing else. If this remains exactly as it is, like just removing the water boil off from one point to one central point, and you optimize everything, you will save energy, water, and all other things. And people will have a much better experience because of this thing. So district cooling, it's a cool thing, it works, but again, you must have realized if you have water scarcity, this does not solve the problem, it just delays it. So how can we solve the problem? Then we come to the awesome Indian technology known as low temperature thermal desalination. Now let this be very clear, more than enough science paper and research paper have thought of it, theorized it. India is the only country that have working models. We have, and again, the problem with this model is that it works so well that people forgot about it. It's like we have discussions with other countries like, how can we solve the water problem? Like, we have it. It's boring. There's an irony of it. It's like, it works so well, we forgot about it for 10 years. It's not like 1 year or 2 years. No, it's been working, we forgot about it. And because here's the deal, desalinating seawater, everybody wants to do this. It's just that, why don't we do it? Removing the cost barrier, you have a brine problem. Meaning, when you are taking water away, you are leaving the salt behind. When you're leaving the salt behind, the concentration of salt goes away from the equilibrium, meaning ocean is salty. Natural life, like be it coral reef, be it fishery, be it algae, all of those ecosystem is trained to work in that optimum equilibrium ratio of salt. If you increase the salt, because it is like, what the hell, it starts to sterilize it. The worst scenario is reverse osmosis. Reverse osmosis has really worst concentrate that it dumps into the ocean. And again, like Israel learned the hard way, that area where they're dumping the brine, that area slowly starts to get sterilized. Like day 1, nobody notices. Day 500, it's like, why this whole area feels a bit off. Day 700, yeah, now you have a giant patch that is fully sterilized. So because again, not that organics cannot handle that sort of salinity, that natural organics that were there, that cannot handle it. So that creates a scenario of really unsustainable system, meaning you can get the water, but you will destroy it. And not to mention, it's a very expensive, costly, and does require a lot of fancy chemicals. Then you have a boiling technology, basically multi-stage flashing, done by places like Saudi Arabia and all that. That has a bit less of a poisonous effect, meaning it can go down to 1.7x, which again, compared to 2, much better. And then you come to the daddy technology, low temperature thermal desalination. This only goes to 1.1x to 1.4x. That's the worst case scenario. Generally, and this plant, it's like 1, not even worse, pardon me, 0.01. Because The Bryan effect can be so minimized in these things that nature does not care, meaning this area is a scenic area. That area is still scenic even though you are doing a desalination plant on that. So it does work. Now, how do this thing work? I have already made a detailed video about it. It's just that you take water from depth, in this scenario 500 meter, and then you take water hot. Hotter water is surface water. So surface water would be 25 degrees Celsius. The deep water would be 10 degrees Celsius. You will have 15 degrees of temperature delta. That delta would be utilized in this puppy, basically a vacuum chamber. So you take the cooling water, it goes into a shell and tube condenser. The condenser is basically, the tubes are cooled by the deep sea water, and then the hot surface water goes into the sprayer. Now, sprayer will not do much in normal scenario, so you pull a vacuum there. Once you pull a vacuum, things starts to evaporate very quickly, and all the heat gets dumped into the cold sink, and then you get fresh water. You collect the fresh water. This puppy works with 1 million liter a day. It's for a small island, so we do not have to worry about that island anymore. So it works. Now, how deep you go, that's up to you. Some designs can go very low. This design is 500 meter, 10 degrees Celsius. Now, you only need to raise the temperature from 10 degree to 15 degrees Celsius, as in like 10 plus 15. You only have to raise it. Now, you do not need 100 degrees Celsius. Why? Because again, partial vacuum. However, that being said, you're like, wouldn't that make it a very sloppy heat sink? No, because A, it's very cold. If you really pull water from that deep, it's 10 degrees Celsius. Your heat naturally wants to go there. You do not have, again, you will get magnificent COP, and plus water is dense compared to air. So it will take a lot of energy just to increase its temperature from 10 degrees Celsius to 10 plus 15. On top of that, it has latent heat of vaporization. That is fixed. It does not care whether you are doing it in a vacuum chamber or you're doing it in vacuum of space or in under pressure. It remains exactly the same. So that's the core benefit of it. The amount of energy absorbed here is bonkersly high. And to give you a rough context of it, what kind of energies we are talking about? If you have 1 megawatt hour of thermal energy, you are looking at 1.5 ton of water production, or liters. Now, let that be very clear. Ton and liters, kilograms and all that remain same, simply because we used water to create those standards. Now we have switched to modern standards, but that's how they started. That's why 1 liter of water was 1 kilogram back in the old days. So generally water, kilogram, ton and all that, they are surprisingly intertransitionable. So you will get 1.5 ton of water vapor. If you condense all of it, ta-da, that much fresh water you're gonna get. So this is a system. It does not destroy the ocean. We have a working experience, not a fancy technology, super simple, just a vacuum chamber, and you are running a wet vacuum pump and cool sump. And in our scenario, all we'll do is like cold water, between whatever cold water have you. Heck, you can even do with surface water if you don't really want to go deep. And take a small portion, very small portion, like it would be like 500 kilograms, 570 kilograms a second. You will only take 70 kilograms. Now, like, why the heck I'm using that weird number? That's the plant. So you take 70 kilograms per second, put that into the condenser of your district heater. That boils it away. Tada. And you're like, that's a very small percentage. That's the core aspect of it. The percentage is so small. The water that you're leaching is so little that it does not affect the wildlife or organic life, so to say. So this is what we call low temperature thermal desalination. This allows us to have the heat sink where we can dump district heat level output, meaning hundreds of megawatt without too much hassle. Although let me be clear, that 1 megawatt hour to 1.5 ton, that's super optimum. Generally, you will still need some energy from going from 10 degrees Celsius to 25 degrees Celsius or higher. But again, you have to temper yourself so you don't do that, because again, you can easily increase that from 0.1% to 1.1 or 1.4. You don't want to do that. You want organics to stay there, so it's long-term sustainable. Now we come to the weird part of it, not even weird, like engineering part of it, which is balance. Basically, we want to save power on cooling, and we will save power on cooling even going to basically district cooling, but we'll lose all the power in pumping. So basically pumping draw, and the deeper you want to pump from, the more energy and the amount of water would be huge. That's the other part. We are draining huge amount of water. So that's there. So from a city's point of view, from a megapolis point of view, the energy content consumption will not change. It will just change where it was being consumed. Rather than being consumed by so many small buildings, it's consumed by one giant plant. So that will change. But we must not be tempted to increase water recovery. We will be like, what if we push it? Because you can easily push from 1% water recovery to almost 30%. You should not do that, because that will create that same cascade failure that other organics are dealing with, where it's like, oh, we roasted and sterilized the whole goddamn ocean, that area, local area. So we have to be very resilient with that. It's like, no, this is a cooling and water is a byproduct. We are not doing this to get water. You have to do that. And give or take 1138 kilograms per second, that gives you, in the current plant that we have working, is 11 kilograms per second of fresh water. So more than enough fresh water. Now what does that translate to? That translate to, with current systems, is if you have 100 megawatt hour, as in like very small district cooling systems, because most district cooling easily exceed that. So you have 100 megawatt hour, that will give you 146 ton of water, give or take a little bit. That is such a large number. We have to use cubic meter, 147 cubic meters of water. That's a reservoir level water, meaning when you measure reservoirs, you measure in cubic meters, and if you're measuring giant dams, you measure in square cubic kilometers. So here it is so much. And again, 100 megawatt is nothing. There are single buildings that will dump that kind of heat. That's nothing. And again, if you are talking about data centers can easily go up to gigawatt hour. So that's nothing. They will generate more than enough water that you can easily have surplus in a megapolis. So that is a very desirable thing. So power draw of the city remains the same. Actually, it does become efficient, because again, instead of hundreds of small compressor working their ass off, they are like, hey, chill, easy, everything easy. Hundreds of electrical network, easy. One heavy place where it's like, no, we're gonna have like very high voltage power line. For example, in hotels, you generally do not send above 135. There you can send 200 or 500 kV line. You're like, no, this is a heavy draw. We're gonna spec it to handle that. And the biggest benefit is water crisis will be solved very severe. Now, this goes true for almost every metropolitan. Generally, they drain water from their, periphery area, so to say. So we used to have a lot of small rivers, and like water, India was very water rich back in the days. So all those were dammed up, all the water drained into metropolitan. Metropolitan is like boiling it away, and people are starving for drinking water, so to say. So that's an unsustainable system. And again, as Mumbai gets hotter, because we already crossed 39 degrees Celsius, certain place 43 degrees Celsius, and again, this is cooler temperatures. We have crossed that long ago. We do need to have a district cooling, so that does not add to basically self-fulfilling hell prophecy, and then get water out of it, rather than just like electricity and water go away, electricity goes away, but water comes in. We want that. It's sustainable long term, and it has the minimal penalty to every system involved. So this was my presentation on how can we solve the coastal city heating issue. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my excitement. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.